Mixtures of gases. Gases behave very differently than solids and liquids. And so sometimes we can treat a gas mixture as though it is just one gas because the identity of the particles don't matter. And so we can measure the pressure, the volume, the temperature, just as if it was a pure substance. And we can calculate the total moles of molecules in that sample, even though they're different molecules. And that's because gases behave independently. It doesn't matter what the particles are. They're going to behave in the same way. But other times we need to think about the individual gases in a mixture. And so what we see, and this is called Dalton's law of partial pressures, and this is the same Dalton who came up with Dalton's atomic theory, is that the pressure of a single gas in a mixture of gases is called its partial pressure. So the gas as a whole, the mixture of the gases, exerts a pressure. And the pressure is due to each of the individual gases. The pressure of one of the individual gases is the partial pressure. So that partial pressure can be calculated from the ideal gas law. We can just rearrange it, and the pressure of that gas N equals the number of moles of that gas times RT over V. And what we know as Dalton's law of partial pressures is that the sum of the partial pressures of all the gases in the mixture equals the total pressure. So you've got a mixture of gases. Each of the gases in the mixture is exerting a pressure. The total pressure is just the addition, the sum of all of them together. Here's a little bit of math showing you how that all works out. So P total is the total pressure. P, A, B, C, those are the pressures of each of the individual gases. So the total pressure is equal to the sum of the pressure of each of the gases in the mixture. Each of those pressures is equal to N RT over V. So you could add all those up. And you can factor out the RT over V, and then you get the sum of the number of moles of the gases. And so the total number of moles of gases times RT over V is equal to the total pressure. The partial pressure is related to the mole fraction of the gas. So if we take the ratio of the partial pressure of the gas to the total pressure, we just showed that the pressure for gas A would be the moles of gas A times RT over V, and that the total pressure would be the total number of moles times RT over V. We cancel those guys out, we get N over N, NA over N total. This is called the mole fraction. So if we're looking at gas A, it's the number of moles of gas A divided by the number of total moles. It's like a percent, except we didn't multiply by 100. So we use chi, which looks a lot like an X, to represent mole fraction. So the mole fraction of A is the number of moles of A divided by the total numbers of gas in the mixture, moles of gas. And then you can take this equation, which we had up here, and you can rearrange it and find that the pressure of the individual gas is equal to the mole fraction of that gas times the total pressure. And that equation right there is pretty useful. Let's put a box around it. That guy right there. So we can calculate the partial pressure of a component from its mole fraction. So we take the mole fraction times the total pressure. Another interesting bit here for gas is the mole fraction of a component is equivalent to its percent by volume divided by 100%. So we say that that's backwards, isn't it? Nitrogen has a 78% composition of air. What kind of a sentence is that? Air is 78% nitrogen? That's what that means. Air is 78% nitrogen. That means that the mole fraction of nitrogen in air is 0.78. Fractions, like mole fractions, are very much related to percentages. It's just a factor of 100. So 0.78 out of every mole is nitrogen. So we can take the total number, the total pressure, sorry, and multiply by the mole fraction, and we get the partial pressure of the nitrogen gas. So at 1 atmosphere, composition of 78% nitrogen, the nitrogen is exerting a pressure of 0.78 atmospheres. So here's an example. To prevent the presence of air, noble gases are placed over highly reactive chemicals to act as inert blanketing gases. A chemical engineer places a mixture of noble gases consisting of 5.5 grams of helium, 15 grams of neon, and 35 grams of krypton in a piston cylinder assembly, forgetting how to read, piston cylinder assembly at STP. Calculate the partial pressure of each gas. What do? What does STP tell us? Standard temperature and pressure. So the temperature is what? 0 degrees Celsius, which is 273 Kelvin. What's the pressure? 1 atmosphere. Okay, so that's useful. And then we have masses of these 3 gases, and we want partial pressure. Well, we could calculate those using something else. We could use the molar volume of a gas, and we could convert these to moles and then do it that way. But I don't think that's what they want us to do. I think they want us to use the pressure of A is equal to the mole fraction of A times the total pressure. I'm pretty sure that's what they want us to do. So what does this P represent? Pressure. Yeah, what kind of pressure? It's the total pressure. So that's the total pressure. So what we need to do to find the partial pressure of each of these gases is to find the mole fraction of each gas. So we need to find moles of these gases, right? Thankfully, they're noble gases, and so there's not really any molar masses to calculate. 5.50 grams of helium. Well, we're just going to convert that to moles. 4.003 grams. 5.5 divided by 4.003. 1.37397 moles of helium. A lot of these gas law problems, there are several ways that you could approach them. That many grams of neon, can't remember the mass of neon, 20.18. 20.18. Zero, that's not a very good, 0.74331 moles of neon and 35 grams of krypton. Krypton's a big guy. But at 83.8. .417661 moles of krypton. How do I calculate a mole fraction? I need to add them all up to find the total number of moles, which is, if I was using my HP, I could do, but I'm not, so alas. I'll have to do it the hard way. So total number of moles, call that N total. By just taking all those numbers and adding them up, it's 2.5349. That's enough moles. So then the mole fraction for each of these is going to be the number of moles divided by 2.53. So if I divide by N total, then I get 0.5420, and this is really sad. I'm boring myself. Wait, I just amused myself. Oh, I'm confusing myself. 2932. 2932. And 0.417661 divided by 2.5349. 0.1648. Those are the mole fractions. X. So X for helium is 0.5420. We would take that mole fraction and multiply it by the total pressure. Since the total pressure is 1, the mole fraction ends up equaling the partial pressure. So for helium, it's this many atmospheres, and that many atmospheres, and that many atmospheres. What would be the pressure of this many moles of krypton? Oh yeah, never mind. No, this is good. Forget that. Any questions? I'll take that as a no. So partial pressures are important in deep sea diving. When you breathe compressed air, you can get abnormally high partial pressures of oxygen in the lungs. And this leads to high concentrations of oxygen in your tissues as well. And the thing about all chemicals, and oxygen is a chemical, water is a chemical, some may be good, there's always too much. There's a spectrum. And so yes, we need oxygen to live, but too much oxygen will kill you. You need water to live, but too much water will kill you. And so if you get above this point right here, 1.6 atmospheres, you get into oxygen toxicity. You get below 0.1 and you get into hypoxia, which means you don't have enough oxygen. So both situations are bad. At the surface, the total pressure is 1 atmosphere. The partial pressure of nitrogen is 0.78 atmospheres, and the partial pressure of oxygen is 0.21. Oxygen comprises 21% of air. At 30 meters, the total pressure is 4 atmospheres. And so the partial pressure of oxygen is 0.21 atmospheres times 4, which is 0.84 atmospheres. And so now you're getting up here towards the upper, I'm sorry, you're still here. You're still okay, but you can see that if you keep going, eventually you can get into trouble. Well, the oxygen's bad, the nitrogen is worse. I think we talk about that later. Collecting gases. The easiest way to collect a gas experimentally is by having it displace water from a container. Do we have a picture? We should have a picture. There's a picture. So this is an illustration of how that could happen. So here we have a reaction going on. We've got zinc and hydrochloric acid, and this is generating hydrogen gas. Here we have a beaker that was originally completely full of water, inverted in this dish of water. It looks a little bit like the mercury barometer, except it's with water and it's not very tall. Then we have a tube coming out of our test tube and going into the beaker from underneath. As long as the edge of the beaker is under the surface of the water will stay there. As the gas comes, it's trying to escape, and it's going to come up and be caught in this inverted beaker, and it's going to displace the water. And in that way, you can trap the gas. Well, here you've got the hydrogen gas that you're interested in, but the water here is evaporating. And so you're also going to have water vapor in there. And so you have a mixture of gases. So there's water vapor in that collected gas. So the water vapor exerts a partial pressure, because all gases in a mixture are going to exert a partial pressure. We call it the vapor pressure, and it only depends on the temperature of the situation. And so we can look this up in a table. We have tables like this. You can find them online with much more information. You can find them in the CRC up in the cupboard there. So at 20 degrees Celsius, the partial pressure, the vapor pressure of water is going to be 17.55 millimeters of mercury. As the temperature rises, more of the water evaporates and the partial pressure of the water increases. So if we're going to study this gas at all, we have to account for the water vapor that's in there. Because what we're really interested in is the pressure and the temperature and the volume of the hydrogen. So we have to calculate out the water. So here's a sort of an example that you might see. A sample of acetylene is collected over water. Anytime you see over water, you're going to have to deal with partial pressures. You have a mixture. The total gas pressure is 738 torr. The volume is 523 milliliters. The temperature of the gas, at the temperature of the gas, which is 23 degrees Celsius, the vapor pressure is 21 for water. So that's nice. We don't even have to go look that up. How many grams of acetylene are collected? So we've got all these numbers. I'm just going to write some of them up here at the top. We have a pressure of 738 torr, and we have a volume of 523 milliliters, and we have a temperature of 23 degrees Celsius. And they're asking for grams of acetylene. With PV and T, what could we calculate about a gas? Number of moles. If we had the number of moles, could we get the grams? Yeah, because here we know what the formula is. But this is a mixture of gases. So the total pressure is 738, but the pressure from the water is 21. So PH2O is 21 torr. How do we find the pressure of the acetylene? We just subtract from the total pressure. So the pressure of this C2H2 equals the total pressure minus the pressure of the H2O. So we've got 738 torr minus 21 torr $717, right? So that's the pressure of the gas. What equation are we going to use to find the number of moles? That one. Yeah, that one, PivNert. PV equals nRT, so we'll rearrange it, and N will equal PV over RT. So we need pressure, volume, R, and T. When we're dealing with PivNert, we have to be really careful with our units. Is this a good unit for pressure? No, because the ideal gas constant is in liter atmospheres per mole Kelvin. So we need to convert this. So we'll multiply by 1 atmosphere over 760 torr. 717 divided by 760. 0.9434, good enough. It should have 3 sig figs, right? Go ahead and keep an extra. You can keep 2 if you want. I ran out of space. Volume is liters. Is liters what we want? Yes, it is. Thanks for telling us. We need to convert milliliters to liters. I was trying to say, is milliliters the good unit? No, it isn't. So 0.523 liters. Divide by 1,000. How about 23 degrees Celsius? Is that good? We want to round that, convert that. 296.15 Kelvin? Yes. Because 298 is 25. Yeah. Yeah, that's okay. I was too. Okay, so now we've got P, V, T, all with the correct units. So we can put these in here. 0.9434 ATM. The volume, 0.523 liters. And the ideal gas constant, 0.08206, with his funky units, liter atmospheres per mole Kelvin. And the temperature, 296.15 Kelvin. That's got 3 sig figs. Okay, 0.9434 times 0.523 divided by 0.08206 divided by 296.15 equals, oh, I got plenty of space, 0.0200303. And that's moles. We need grams. So we need the molar mass of this guy. There's 2 carbons and 2 hydrogens. (26.036). So that's moles. We're going to multiply by 26.036 grams per mole. And how many significant figures should we have? 3. So we end up with 0.529 grams of C2H2. Any questions? Everyone's dazed. So what made this calculation different than what we did last week is that we're now talking about a mixture of gases. And the big clue here is over water. and they talked about the vapor pressure of water. They wouldn't have to say that, though. They could just say that it was collected over water and give you the temperature, and then you have to go look it up in a table. You do not need to memorize vapor pressures for water. If you need them on an exam, they'll be given to you, either in a table or directly in the problem like this one.